Hello maths fans! Dr. Tom Crawford here at the University of Oxford, and a huge welcome to anyone joining us from the Tuesday extravaganza over with Matt Parker, Steve Mould and Numberphile. In the Tuesday video, I explain how to cut a pizza into 22 slices using only 6 cuts, which I claimed was the maximum possible number of pieces you can make. In this video, we are going to look at the problem in more detail and derive the general formula for the maximum number of pieces a circle can be divided into using n cuts. As with most problems of this type, let's start by looking at some small values of n and see if we can spot a pattern. So if I take this to be my circle or pizza or any other circular shaped piece of food or even object, so when I only have one cut, there's only really one thing I can do. So for one cut, I'm going to get two pieces. So if we record this over here, I can say number of cuts versus max number of pieces. And what we've seen here is when we have one cut, we get 2 pieces. Now, if I'm allowed a second cut, so n is now going to be equal to 2, then I've actually got a choice to make. So I could do the cut here, and this would give me 3 pieces. One, and then this one would be divided into 2. However, we're trying to get the maximum number of pieces. And probably from past experience cutting cakes or indeed pizza, most of you will know that the best thing to do here is actually going to be to pass through our first cut, and this allows us to get 4 pieces. And this is going to be the maximum. So for 2 cuts, we can get 4 pieces. For 3 cuts, we again have a choice to make. We could decide to cut through here, hitting one of the previous lines. I could also add something up here which wouldn't intersect any of those previous lines. However, remembering we're trying to get the maximum number of pieces, what I'm actually going to want to do here is intersect both lines with my third cut. So if I do something like this, then what we can see is I now have 1, 2, 3, 4, 5, 6, 7 pieces. And this is in fact the maximum. Now let's just stop for a moment and think a little more carefully about the decision that we just made. So when adding this third line, I said I could go up here and avoid any of the previous 2, and that would divide this top region into 2 pieces and therefore add 1 to the total. I could have also drawn something like this, which would intersect one of those previous 2 lines, dividing the top one into 2 and the bottom one into 2, so adding 2 to our total. And then the one that I've drawn actually intersects both lines that were already present, and this divides this region into 2, this region into 2, and this one into 2, adding 3 to our total to give us what is the maximum of 7. So I think we've actually spotted something really important. It seems that in order to maximize the number of pieces that we can get, we actually need our next cut to intersect all of the lines that are already there. So let's use this now and try it out for n equals 4. So I want our 4th line now to intersect the 3 that are already present. So I'm going to add it sort of here. So it intersects 1, 2, and 3. So it intersects the 3 lines that were already present, and counting up these regions, I'm going to get a total now of 11 pieces of my circle. And we can continue with this exact same method for n equals 5, 6, and higher numbers. So for example, when n is going to be equal to 5, I need to add my 5th line. Remember, our approach so far says to get the maximum number of pieces, I need to cross as many of these lines as possible, because every time I cross a line, I move into a new region, and therefore I'm dividing up that region. And so to get the maximum number of pieces, we want to break up as many regions as possible, which here ultimately means intersecting as many different lines as possible. So when adding this fifth line, I want to intersect the 4 lines we currently have. So let's see how to do this. I'm going to need to, let's think about this. So I've got that one, that one. These get tricky the more lines you have. So we need to intersect all 4 lines. What if I did, I could do something sort of like this, I think. I think something like this will work. So that's 1, 2, 3, 4. Okay, so if I add my 5th line as shown, then I've hit 1, 2, 3, 4. So I've intersected the 4 lines already present, and I know that's going to therefore add an additional 5 regions to give me a total there of 16. And I will just count these just to convince you and just to be sure that this is working correctly. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 regions, each one has a dot. I just counted them out loud. We have 5 cuts, and we can see there is indeed 16 pieces, and that is going to be the maximum because of the reasons I just explained about needing as many intersections as possible to generate as many new regions as possible. So now we have the solution for some small values of n. Let's see if we can spot a pattern and come up with the general formula. So the first step is going to be to look at these numbers and see what's happening in terms of the difference between consecutive entries. So for example, here we're adding 2, then we add 3, then we add 4, and then we add 5. So at each step, we are adding 1 more than we previously added. But not only that, if we actually look at, for example, step 4 here, when n is equal to 4, the answer for the maximum number of pieces is the previous answer plus 4. To get the answer for n equals 5, it's the previous answer plus 5. So what we've got here is actually a type of recursion relation. And we're going to write down a formula using that kind of approach. Let's define a function f, where f of n is going to be equal to the maximum number of pieces for n cuts. So our input is the value of n, the first column of our table, and the output, f of n, are the values in this second column, and of course that's what we want to know. Now, again, if I look at step 4, it's the previous value plus 4. Step 5 is the previous value plus 5. So using this notation, I can actually say that f of n is equal to the previous value, which is f of n minus 1, plus n. And this will work for all of the values in our table, and it will generalize for higher and higher values. So now we know the value of fn in terms of the previous value, f of n minus 1. But there's nothing special about plugging in the value n. I could have started with n minus 1. So f of n minus 1, I can say up here, is equal to the previous value in the table, well that's just f of n minus 2, plus n minus 1. And then f of n minus 2 is just equal to the previous value in the table, which is f of n minus 3, and then I add on n minus 2. And I can just continue in this way. And eventually we'll get to, for example, f of 2, which is equal to the previous value, f of 1, plus n, and here n is 2, so plus 2. And of course, f of 1 was our first line, so one cut on the circle gave us 2 pieces. So that's equal to 2. So what we've done is to work from f of n in terms of f of n minus 1, which is some general value, any value of n. And then we can actually express n minus 1 in terms of n minus 2, and we can just continue to count down, knowing that no matter how high of a value of n we start at, we will eventually get down to f of 1, and we know the answer for f of 1. We actually now have all of the information we need to get our explicit formula for fn, and we do this using backwards substitution. So if I start with this formula, we know that f of n is equal to n plus f of n minus 1. But f of n minus 1, we know that's equal to f of n minus 2 plus n minus 1. So let's keep the n minus 1 term, and then let's substitute again for f of n minus 2. But again, we know that f of n minus 2 is n minus 2, so we'll keep that one, and then plus f of n minus 3. But f of n minus 3 is n minus 3 plus f of n minus 4, and so on and so on. So this will be plus dot dot dot. We will eventually, just as we did here, get down to f of 2, which is f of 1 plus 2, which is 2 plus 2. So this will continue with the numbers decreasing by 1 until we get to 2, and then we add 2 at the very end. Now, this is indeed an explicit formula, but we can actually make this a little bit nicer to calculate. So what I'm going to do is take the number 2, and I'm going to replace it, and prepare to have your mind blown, with 1 plus 1. 1 plus 1 is equal to 2. Now, there is a reason I've done this, because now the first n terms here, with these two as well, are actually just the sum of the first n integers. So I can rewrite this and say f of n is equal to 1 plus the sum from k equals 1 to n of k. Now this is a famous sum. It is known as a Gaussian sum because Gauss worked this out when he was a child at school, and he was given the task by his teacher to calculate the sum of the first 100 integers to try and keep him occupied, but he actually spotted a very clever pattern. And the pattern relied on averages. But what we just need to know here is we have a formula for this particular sum, and it's equal to 1 plus, and then we've got a half n times n plus 1. So our final formula for f of n is given in this box. F of n is equal to 1 plus a half n times n plus 1. Now hopefully some of you will recognize this formula from the Tuesday video, and if I plug in n equals 6, just to double check, so f of 6 is equal to 1 plus a half n, so that's going to be 3 times 7, which is 1 plus 21, which is 22. So our pizza with only 6 cuts can indeed be divided up into 22 pieces. And now, purely for your entertainment, here is some more footage of me trying to cut an actual pizza into 22 pieces. We have a pepperoni pizza, we have a pizza cutter, and I have 6 cuts. Let's see if I can make 22 pieces. So the first one doesn't really matter. Let's just kind of go right through here. Okay, so that's a solid 2 pieces from 1 cut. Now, what should we do next? Let's try, this is going to be really difficult to cut this. I'm going to try my best. Let's try and do one sort of here. Okay, so this is going to be number 2. Okay, 4 pieces, so far so good. I'm going to now try, so I've got to go through 3 of them. So let's go here. Okay, there are going to be some tiny pieces of pizza. So I now need to cross the 3 of them. So let's go over here and do it like so. So this is pizza cut number 4, right through there. Okay, I'm getting pizza everywhere. Okay, right, 5. Now it's tough. I need to go through all 4 cuts. Okay, so I've got like 1. How am I going to do cut number 5? So I've got to go through. This is much harder in practice than it was drawing it on a board. This is not going well, but I think I've got an idea. If I kind of go through here, the edge of that one and then the edge of that one, the 2 tiny little pieces, I think that's going to give me the 5 that I want. Tiny little piece in there. Now for number 6. Oh god, this is like impossible now. So I've got to cut through all of them. So 1, 2, 3, 4, 5. This is not going to go well, but I can try it. So I think if I cut here, kind of go 1 through that one, through that bit, through there, sort of like that. I think. So having now tidied it up a little bit, I'm going to give them a final count. 1, 2, 3, 4, 5, 6, 7, 8, 9, little tiny one, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21! That is a good effort. I am claiming a good effort. Unfortunately, it's not quite the 22 I was hoping for, but almost. Improvement to be made by someone watching this video. I want to see if any of you can cut a pizza into 22 pieces using only 6 cuts, and I expect photographic evidence. Enjoy. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and a huge thanks to Matt Parker, Steve Mould, and Brady Haran for putting this all together. Take care.